intrinsic or pure semiconductor. In this semiconductor, number of free electrons and number of holes will be equal, and these numbers are written as Ni, number of charge carriers in intrinsic type. I stands for intrinsic. So Ni means number of free electrons or number of holes in a pure semiconductor. Why these two numbers are equal? As one electron becomes free, it creates one hole. So therefore these two numbers are equal. And this number is temperature dependent, and it is found to be depending on temperature like this. So this is the expression. So it is depending on temperature as A is a constant, T raised power 3 by 2, E raised power minus E gap over 2 kT. K is Boltzmann constant and T is again temperature. Two types of impurities are doped to change the conductivity of a semiconductor. So we have seen conductivity changes as temperature changes. The other method of changing conductivity is mixing some impurity in semiconductor, and when we deliberately mix impurity, that is called doping. So two types of impurities are doped. One is pentavalent impurity like phosphorus, antimony and arsenic, or trivalent impurity like aluminium, indium, boron, etc. When these impurities are mixed in a semiconductor, in molten state it is mixed thoroughly and then resolidified, then it is seen that these pentavalent impurities or trivalent impurities, these atoms, these impure atoms just take place of silicon in the same structure, in the tetrahedral structure. This is energy diagram of sodium atom. Its configuration is 1s2, 2s2, 2p6, 3s1. It carries 11 electrons, and 3s is half filled as it's carrying just one electron, though its capacity is of 2 electrons. According to Pauli's exclusion principle, no two electrons can have same set of quantum states. The two electrons filling in 1s level have opposite spins. So these two electrons, they have opposite spins. So no two electrons can have all the quantum numbers as same. There are 4 quantum numbers, n, l, m and s. So for these two electrons, n, l and m, these are same, but s is different. For one electron, s is plus half, for the other electron it is minus half. So this is how electrons have different quantum states. These are two atoms which are widely separated. These atoms, they do not interfere with each other. So Pauli's exclusion principle is applicable to electrons in same atom. Pauli's exclusion principle is applicable in this atom and independently in this atom. Pauli's exclusion principle is not applicable to these two electrons because these two electrons are of different atoms. So these two electrons can have entirely same quantum states. But when the atoms come close, as in a solid, the atoms start interacting, and the Pauli's exclusion principle is now applicable to the group of atoms rather than for each atom separately. So what happens when the atoms come close? Then Pauli's exclusion principle is applicable to the group of atoms. Now these two levels will have to be at a different positions, so that now these two electrons can have different quantum states. If the levels were at the same position, then here there are two electrons. Those two electrons will have exactly same quantum state, which will violate the Pauli's exclusion principle for the group of two atoms. So therefore these levels will have to be at a different positions slightly, like this. Now there are 4 atoms, and when they come close, again their levels slightly change so that they are not in the same position. And similarly, if we have many atoms in a solid, say 10 to the power 20 atoms, then those 10 to the power 20 atoms will have their levels so close, very close to each other, and that will form a band rather, and then the energy level diagram converts into a band diagram. So for sodium atom, the band diagram is shown like this: 1s, 2s, 2p, and 3s. And since 3s is half filled, so it is shown like this. The completely filled bands, they're called valence bands. All these bands are valence bands, the completely filled bands, and we are mainly interested in the uppermost band. And similarly, bands having some empty states. So those bands which are either fully empty or partially empty, they are called conduction bands. And sodium is a monovalent conductor because these electrons which are in conduction band, they can easily jump into these empty states and conduct electricity like this. These are one electron of 3s level, one electron of 3s level in every sodium atom. And these levels can contain at most two electrons. So there can be two electrons in these levels. And as of now, they are having just one electrons. And suppose we apply an electric field in this direction. So this electric field will apply force, opposite force on electrons. And the electrons can respond to those electric field and can jump into these levels like this. So the electron of this orbit can jump into this because there is a space here. If it was full, then this electron could not jump. Then this electron will have to jump to the other orbit, the next orbit, which obviously is empty, but jumping into that orbit would require energy. So normally that would not happen. So electron in same orbit can jump easily without requiring much energy. So therefore, sodium is a conductor. This is the case of zinc. It has 30 electrons and its configuration is as shown. And if you see the last few configurations, that is 4s2, 3d10, and 4p0. It seems that 3d is full and next orbit 4p is completely empty. So when these levels convert into bands, it seems as if 3d will be a full valence band and 4p will be a completely vacant conduction band. But actually it's not so, because when these levels convert into bands, these bands kind of overlap, and there are many vacant levels available for these electrons in 3d, for which jumping into those levels requires no energy. So electrons in 3D band, many electrons in 3D band can easily now jump into 4p band, because many levels are in fact at a level having a lower energy. This is an example of conductor. So zinc is a conductor. It's a bivalent conductor because in fourth orbit, there are two electrons. So it is a bivalent conductor. This is band diagram of insulator or semiconductor. In both cases, valence band is full. Conduction band is completely empty. And the difference between these two bands, the energy difference, that is called energy gap. Energy gap is more than 3 electron volt in the case of insulator, and it is less than 3 electron volt in case of semiconductor. And in particular, it is 1.1 electron volt in silicon and 0.7 electron volt in germanium. So in insulator, since this energy gap is a larger gap, the electrons cannot jump into conduction band and there is no conduction in the case of insulator. While in semiconductor, when the gap becomes smaller, like 1.1 or 0.7, then due to temperature, many electrons get enough energy to jump into conduction band, and as temperature is increased, conduction is possible in semiconductor.